Hello and welcome back. And so now we want to talk about where is the energy coming from in either nuclear fusion or nuclear fission. And it has to do with what's referred to as the binding energy. So let's first talk about chemical binding energy. And so in a particular atom, you're going to have the nucleus, which consists of the protons and the neutrons, and then going around it are going to be the electrons. Now, it's not like little planets going around the sun. Remember, it's more like a cloud of electrons that are going around this thing, so we're not going to get into that again. But just remember that these electrons have a particular orbit around the nucleus. And so there is a electrical force, the force of electricity, that is holding the electrons in their orbits because the nucleus is positive because of its protons. The electrons are negative, and so opposites attract. And so there's going to be a certain amount of energy associated with these electrons going around the nucleus. And so let's now say that you've got two atoms. So here's another atom down here, and it's got its electrons going around. And so these electrons see this positive nucleus and they're attracted to it. And these negative electrons see the positive nucleus down here and they're attracted to it. And so that's what's going to hold two atoms together to make a molecule, like water. Water is H2O. So it's got two hydrogens and it's got an oxygen. And they're being held together by these electrical forces. So that means that if you want to pull this thing apart, it's going to take a certain amount of energy to do it. And that's going to be called the chemical binding energy. Now there's also nuclear binding energy. So in this case, you've got the nucleus here, and those protons and neutrons are glued together by the strong nuclear force. And so if you want to pull that nucleus apart, let's say it's nuclear fission, and you're pulling it apart, it's going to take a certain amount of energy to do that. And so we're going to call that the nuclear binding energy, and that's the energy that's being released in a nuclear reaction, whether it be nuclear fission or nuclear fusion. But the nuclear force is 100,000 times more powerful than the electromagnetic force. They don't call it strong for nothing. So it's 100,000 times more strong. And because of that, that means the energy released is going to be 100,000 times more powerful than a chemical reaction. Okay, now how is that release of energy manifest itself? So here we have an example. The first picture there is an example of a nuclear fission reaction in which you've got uranium, and then it breaks apart, and then after the nuclear reaction, you're left with some krypton, and then you're also left with some barium, and then you're left with some extra neutrons as well. Okay, now let's pretend that we live back in the time of Sir Isaac Newton, like 400 years ago. And he would conduct an experiment like if he took his pen or his quill or whatever, and he put it on a scale, and let's say that it read 10 grams. And then what he would do is he would take the top off, and he would, again, measure the mass of this pen, and it would turn out to be 9 grams. Can you figure out how much this would have to be? 1 gram. So you took the 10 minus 9 has to be 1. And so Sir Isaac Newton would say, what's the big idea? So after uranium breaks apart, if you were to weigh all the pieces parts that are left over after the nuclear reaction, it has to equal the mass of the uranium. So that's what Sir Isaac Newton would say, and he was wrong. So he didn't know anything about nuclear power. But anyway, that's probably what he would have said. So what really happens is that if you were to weigh all the pieces parts after the nuclear reaction, it's going to be less than the amount that you started with. And the same thing is true for a nuclear fusion reaction. So the second picture shows the 4 protons that go into a nuclear reaction. They're smashed together and they're turned into helium. And if you compare the mass of the protons that you started with to the helium afterwards, you notice that there's less helium. The mass of the helium is less than the mass of the original particles. So how could this possibly be? Well, that missing mass is what's turned into the energy of the explosion. And so Albert Einstein came up with this very famous formula that says E equals mc squared. E for energy equals the missing mass, that's the m in the formula. And then if you recall from Unit 1, we talked about the speed of light. So that's the letter c, and that's equal to 3 times 10 to the 8th meters per second. So that's the speed of light, and we have to square it. So it's squared in that formula. So that's how we calculate the energy that's released. And so that missing mass is basically that binding energy that was being used to hold that nucleus together. All right, let's do a worked out example of how to use this formula. So you notice that the formula has the red box around it, so that would mean that I would want you to be able to actually plug numbers into that formula. So let's try it. So we're going to go back to 1945, and when the atomic bomb was dropped on Hiroshima at the end of World War II. And that bomb contained 64 kilograms, which is equivalent to 141 pounds of uranium. So if you go to New Mexico, you can go to Los Alamos Labs. They have a museum where they have a mock-up of the 2 atomic bombs that were dropped on Japan during World War II. And so the actual bomb that was dropped was, I'd say at least 6 feet, 7 feet, 8 feet long, or about 2 meters. So it was a very large bomb that was dropped. But the warhead, the thing that actually blew up, was a chunk of uranium that was 64 kilograms in mass, and it was about the size of a soccer ball. So if you can imagine a soccer ball weighing 64 kilograms or weighing 141 pounds, that's pretty dense. But then what did we say about the nucleus? The nucleus of an atom is pretty dense. So that's the reason why that uranium was very dense. So after it exploded, only 0.7 grams of the uranium was actually turned into energy. Well, what happened to the other 63.3 kilograms? So what happened to it? So it was turned into fallout. So all of that remaining uranium became radioactive fallout. So only 0.7 grams was turned into energy. Now, to give you an idea, that's a paper clip. So I've got my paper clip here. Can you see it? What color is it? It's an invisible paper clip. Okay, red. All right, so it's a red paper clip. Anyway, a paper clip has a mass of about 1 gram. And so here you've got 0.7 grams was turned into energy. Well, how big of an explosion was that? So we write down that the mass is 0.7 grams, but that's the wrong unit. The official metric unit is not the gram, it's the kilogram. So we got 0.0007 kilograms. And we want to know how much energy was released, so that's the letter E. So our formula says to take the mass, 0.0007, times the speed of light, which is 3 times 10 to the 8th, squared, so we have to square it. So on your calculator, 3 times 3 is 9. And then what do you do when you square a exponential? The 10 to the 8th, you multiply the exponents. So you end up with 9 times 10 to the 16th. And now we got to take that number and we got to multiply it by 0.0007. And so that ends up being 6.3 times 10 to the 13th joules. The joule was the official metric unit for energy that was of energy that was released when that bomb exploded. And that is equivalent to 15,000 tons of TNT exploding. So to give you an idea what that means, at the end of World War II, we were sending 1,000 B-29 bombers to Japan, and then each one could drop about a ton of TNT. And so that one bomb that we dropped was basically equivalent to an entire 1,000 bomber bombing run of Japan. And so we dropped 2 of them on Japan, and then that finally they decided to surrender after that. So that's an example of physics and history coinciding. All right, I've got a little video here that I want you to watch, and it's called Nuclear Explosion Power Comparison. And so it's only 3 minutes and 59 seconds long. And so see if you can find that on the internet, and it will compare different kinds of explosions and show just how much energy is released by each one of them. Okay, so when you've done that, in our next segment, we're going to switch gears and we're going to start talking about the sun.